occupies most of Eastern Asia.
Right, okay.
Yeah.
That's weird that they don't trade in yuans or whatever.
No, it's not a global currency. You need to be using either euros or dollars.
No, but for petrol, it's only for oil. It's only dollars. They're only
Yeah,
allowed to
because
trade in dollars.
dollars is the closest thing you can have to a global currency.
Yeah.
You know,
But it's also because of
the last thing you want to
petrol,
do is trade in the local currency of the people you're selling your product to.
Right.
Okay, because imagine you were trading to South Africa, for example. What's the currency there?
Oh,
Yeah, that was a good example. What's the currency?
17.5
Yeah,
to 1.
like I could be trading. I could trade him oil. I could get his money, and then the
Yeah,
next
well,
day,
yes.
the
That
next
money,
day he
yeah.
could devalue his currency, and I've been suckered then.
Yeah.
So you want a currency that the buyer can't have any influence over.
But then why
Yeah.
don't we trade in euros?
Well, that's actually been an interesting idea that some countries have looked at trading in euros. Now, Iraq was considering trading in euros. Interestingly, the Americans invaded. I'm not saying the two are connected.
Syria.
Iran is also considering trading in euros, and Syria too, is it? I think-
Syria, yeah.
Are you sure?
Mubarak wanted to. Was it Mubarak?
No, I don't know if that's right because I thought Syria. Oh, maybe actually, maybe no, you might be right.
Something about, I'm sure.
You might be right. Anyways, I don't think the Americans would tolerate current countries trading oil in euros.
But for example, if a big country like China starts trading in euros, what are they gonna do? They can't do anything.
Yeah, but China's currency is tied to the US dollar.
Oh yeah, they have a lot of.
No, the actual isn't the Chinese currency fixed to the dollar? US dollar. Like what is it now? Is it like 10 equals $1 or something?
No, it's 6.8 or
Is $1 US dollar.
yeah.
And this is fixed by the government.
Yeah.
Yeah, isn't it? I think so. So it wouldn't make sense for China to trade in euros because they're basically using dollars, All right, we'll continue now.
Interesting.
Keplers Law. Or rather, it's Kepler's 3 laws to be more precise. Now, this is interesting. Has anybody actually heard of Kepler? You've heard of Kepler, Lynn?
Only the name.
Only the name, okay, yeah. Anyone else, even just the name, Kepler? No?
Heard of it.
You sure, yeah?
Can't remember what his name is.
Yeah, and you see, it's unfortunate because Kepler was before Newton. And, yeah?
It's
Oh, you're thinking, no, but they're, yeah, maybe you're mixing up with Doppler. Yeah. Anyways, it's a little bit unfortunate that more people don't know about Kepler because in some way what Kepler did was a little bit more impressive than what Newton did because Newton obviously was a genius and he had lots of time and mathematics to help him. But when Kepler started his studies, there wasn't really a good understanding of physics. Before calculus, before Newton, and so I think what Kepler achieved was quite insightful. So what did Kepler figure out? Now remember, Kepler figured this all out from just looking at data. Kepler had records of planetary motion and their times and their orbits, He wasn't doing equations like we were. He was just looking at numbers. The first thing Kepler noticed is that bodies orbit the sun will move either in a circle, okay, that's fine, or an ellipse. So Kepler noticed that you can have circular or, as more common, elliptical orbits like this. Now this can be proved from Newton's law, but let's remember Kepler is before Newton. Okay, But it's a little bit too difficult for us to prove it, but you can prove that this law means that you get these types of orbits. Okay, so there you go. You can write this down. This is Kepler's first law. Now, of course, because Kepler is just as good as Newton, he too must have 3 laws. I'm sorry, Kirchhoff, with your 2 laws. You're just not in with the big boys.
Lineage in China, what do they call these laws? Like, surely, I guess they don't have a Western name.
No, I think it just gets translated. It
Yeah,
probably
yeah.
sounds similar to Kepler.
Yeah, yeah.
So like
So-
Newton, what's Newton in China?
Don't.
Yeah, so it's practically the same.
Kepler is Kepler.
Yeah, it's
But
no
I would
difference.
think that you use some Asian mathematician,
I don't.
similar
In cases where there was an Asian mathematician beforehand, yeah.
even regardless, I would think.
So like, China has their version of Pythagoras, I'm sure.
Yeah.
Yeah.
Something like, I don't know, Go D or something. Who's the Chinese Pythagoras?
Pythagoras.
The guy like Pythagoras in China.
Yeah.
You must have some version of him. You know what I mean? No. Long time ago, he loved triangles. Like,
I think there was mentions, like, I just learned from the British.
is it? So it sounds something like Go D or some.
In that England?
Let me see.
No. Do you know what I'm talking about?
Google things.
Yeah. What's this?
Oh, Google. Go.
Go.
What's his name?
Go.
Goku. Sounds like Goku or something. Yeah. Anyways, I guess Kepler and Newton, there is no equivalent in China. Okay, have you got that first law? Where was Kepler from? Was he Swiss? I'm not sure. Did you find him?
I don't know. The oldest Chinese mathematical text.
All right, that's okay.
They didn't name that by his name.
Oh, it's not named after him.
Or
No,
his-
it's like
Johannes Kepler.
Yeah, what country is he from?
German.
Oh, he's German. Oh yeah, Johannes. Okay, continue. Now you all knew. Well, actually, I don't know. Did you know that the orbit could be elliptical?
Yeah.
Yeah, you knew that
I would
already.
think it's more elliptical than circular.
we learned.
There's,
In most cases, it's
yeah, I
always
think,
elliptical.
yeah, maybe Mercury might be pretty circular.
Yeah.
Yeah.
Yeah, it seems to be actually the further out you are, the more elliptical it could be. Yeah. Right, continuing. Proof is too difficult here. Right, so Kepler's second law states that the area swept out by an orbiting body per unit time is constant. Now, what does that mean? I can give you 2 versions. I'll give you a formula. So as a formula, basically it means that, well, there's a couple of ways to state it, but one simple way to state it is that V1 R1 equals V2 R2. So in other words, if you're moving in an elliptical orbit, will your radius be the same?
Yes.
No. Because obviously, like if I go back to the picture here, if you're here, you're further away than you are here. This has the effect of changing your speed. So if I go now back to my second law,
Also, the closer you are, the
The
faster.
smaller.
that's it. The closer you are.
It's
No, hang on. You have to think about this. If you're far away, the radius is bigger, and if you're closer, the radius is smaller. So the v has to always be the opposite to keep the equation balanced. So if this R1 suddenly gets smaller, the v has to get bigger to compensate. Yeah. So yeah, as you're saying, Diego, when the Earth is here, is traveling faster than when the Earth is here.
Because when you are there and then you start going towards the right, so going, it starts accelerating.
It speeds up. Yeah.
and then
Yeah.
slows down.
But that's only one way to state it. There is a nice picture way to state it that I like. So imagine you look at the movement over a period of time. And the period of time doesn't matter. You could look over 1 month, 1 day, 1 week, it doesn't matter, okay? If you calculate the area here in a 1 month period, that is a constant. If you calculate the area here in a 1 month period, this area will equal this area. It's a constant. Okay, that's what Kepler originally said, that the area swept out is a constant. As a formula, it actually is this nice little formula here. I won't prove the result. That's a lie. I won't prove it. I used to, but no.
That's, how do you work out sections of areas on an
I
ellipse?
approximate it as a triangle.
Yeah. Because of the curve.
Yeah.
So,
Insignificant over a small period of time.
but it's hugely significant on the scale of the distance between Earth and the Sun,
Yeah, yeah.
even for a second.
No,
How fast is it
no.
orbiting the Sun?
Oh, we're talking about kilometers per second.
Yeah.
265.
No. All right. Have you got that? Have you got that? Guys? Yeah. Okay, continue.
Yeah.
Kepler's third law states that the periodic time squared is proportional to the radius cubed. That is, t squared is proportional to r cubed. As a formula, it's this. Now, before you write that down, please note, remember we said Kepler is before Newton. So Kepler would never have written it like this, because Kepler didn't know G, M. You know, he didn't know. So for Kepler, he would have had this whole number here as one constant. Do you know what I mean? He didn't understand that this was made of 4 pi squared over gm. For him, it was just a number that he calculated, that he got from his data. Okay? It's more convenient for us to use this. Alright. The proof of this is on the exam. Yeah. And so I will now prove it. That means the proof is on the exam.
Did it ask you to actually?
Yes. They could ask you to prove this formula.
Usually in the B or the A.
Both, actually. Both. The proof's not that bad. I'll show you it now. We basically use our buddy Newton and circular motion. Are we ready for the proof of this? Yeah? I think the relationship is kind of interesting, isn't it? Like, it's not a relationship you could guess, you know? You might guess a relationship like T is proportional to or maybe T squared is proportional to or. You wouldn't never guess T squared is proportional to or cubed.
Is it average law?
Yeah, approximate it as a circle. Yeah. Average or, technically. Right, let's look at the proof. So, you have an M, you have an M, and around they go. So, we're looking for a formula for T, really. So, T equals 2 pi over omega. But F equals m omega squared or. But F equals GMM over R squared. Now, I can make these equal. I get M omega squared R equals GMM over R squared. Cancel, cancel, and I get R cubed omega squared equals GM. Now it's time to use this guy. Okay? So what I'll do is I'll just change him into omega squared equals 4 pi squared. Let's try that again. I'll just change him into omega squared equals 4 pi squared over t squared. What's that? Is someone saying happy birthday?
Yeah. 3 p.m.
Right. So if I sub in the omega squared, I get 4 pi squared over t squared or cubed equals gm. So now I get t. So now I get t squared equals 4 pi squared over gm or cubed. End of Kepler's third law proof. And in fact, of all the proofs on the exam, this is the most common one to ask. Now, it's not too bad. I mean, it's not even as hard as the one I did earlier today with the potential energy. You got that proof?
2 seconds.
Okay. Yeah? Continue? Continue, guys? Yeah? Okay. So, Diego? No? Yes? Okay. So, a little bit of vocabulary now. Does anybody know this meaning? The meaning of this? A geostationary orbit is also called a parking orbit. Does anyone know what this is? Yeah, but that's not. I understand why you're saying that, but that doesn't quite make sense because it has to be moving. It's in orbit.
Isn't it what
Like
the
it's
international
really-
space station is doing?
Yeah.
They are
So,
on a
It's
set
moving in-
distance from the.
yeah, you all understand it, but there's a very nice way to say it. Go ahead, Gina.
such
No?
that it doesn't move further away from
Ah, yeah, but that's so awkward.
Constantly.
No. The orbit has a periodic time t of 1 day. If it's in a geostationary orbit, then its periodic time is also 1 day. It keeps it matched up with the Earth. So it just means t is 1 day. That's all. Right? Now I have to check this. I used to think that GPS satellites were in geostationary orbit, but I don't think they are. But I do know what is in geostationary orbits for sure. Satellite TV.
Oh, yeah.
They're in geostationary orbit. They need to be, because otherwise you'd have to move the satellite dish on your house. So the satellite TV is in geostationary orbit. Now it's funny actually, satellite TV will probably become less and less popular as just more and more people get high speed
Yeah,
broadband and
but you
things.
still need them for telecommunications and stuff.
Yeah, but so they might not be a private.
Oh, yeah.
They might just become used by internet providers and telecoms, you know. But I mean, your mobile phone doesn't use a satellite.
No,
Once
but
they
then you have
launch a
Inmarsat
rocket.
and stuff like that.
Yeah. Huh?
How do they make a rocket orbit, or just make a satellite orbit something in a fixed position?
Lots of maths.
Lots of maths. Yeah, no, he's right. You have to have the rocket release the satellite at the right speed and the right height. You know.
To have a trajectory.
Yeah, exactly. Yeah, yeah. And usually the satellites sometimes have little thrusters on them to adjust if necessary,
And then to crash when they are.
and then to burn up when
So
complete. Yeah.
then you get like a bad signal or something. Is
That's-
it,
No, not
No,
too.
not
It's
It's
not
interference between the.
So
no-
satellites are reliable.
What if they're just like moving a bit because of other factors? And
So there's a couple of things that would interfere with. You mean like your TV satellite?
Or bad weather.
Bad weather,
yeah, but
obstructions.
any influence from outside, because it's already in space, it couldn't be due to.
No, I don't think it'd be clear enough from space. All the interference would be local.
Well, for example, they are used with for like super high speed. I know, like a big football match. They use them to.
Oh yeah. That's what I'm saying. Satellites would probably only be used by private operators, like broadcasting sporting events and things. Yeah.
The Olympics are all retransmitted by.
Yeah. And you find it strange. Like a lot of people in my housing area still have satellites.
Yeah.
Now I think a lot of the reason is because a lot of them are Polish, so they want to get the Polish TV stations.
Now
You
you
know.
can do it through internet.
I know. Yeah. Like I have loads of channels at home.
And I actually watched a video recently saying that TV antennas are coming back.
Are they?
Yeah,
No, I don't
because
believe that.
People want to introduce like 4K satellite TV
Oh, okay.
as a standardized.
Again, yeah, but do you really need 4K in your life? Do you?
But
Well,
you can also retransmit 4K with like
You can use
fiber
fiber
optics
as well,
and
yeah.
fiber optics now.
Yeah. So I don't know. It's hard to see the future of satellites being used for TV, anyways. But at the moment, they're still used in geostationary orbits for signals. So it has the effect that when you look up in the sky, it's like the satellite's not moving. It's like it's sitting there. Now, of course, it is moving. It's just moving with you. But it looks as if it's just sitting up there. So you can point your satellite dish at it and get the signal. You know.
If you know where the satellite is,
Yeah.
it's quite easy to disrupt it.
No, because the satellite. No, as long as you can still point to the satellite and see it, you can get the signal.
The wave that comes off the satellite is also moving with the Earth.
Yeah.
So it's not like, otherwise it would be like shooting a bullet.
Oh, do you know what? I
From a
don't know.
moving
No,
car.
I don't know. I don't know actually, because it might be the case that it's not,
Yeah.
but because the time is so small,
Yeah.
you can't see the effect of it being off course.
So maybe there is, but it's so small that
Yeah, I would say so. I'd say
I always
so.
thought about that, the logic, because in like games like Grand Theft Auto,
you're
when you drive in a car and you're shooting a gun out the window,
They have the effect of the bullet.
the bullet stays in where it was fired from. So because the bullet would actually move with the same speed that the car is moving, right?
I don't know if the bullet would still move. I don't know.
I think you've already.
If the bullet has left, it would have some speed in the direction the car was going at.
Yeah.
but also you have
Yeah.
the wind affecting it, so it will
Uh,
But then it's already cut in three.
Yeah, I don't know how realistic the people in Grand Theft Auto
No, that's what I'm saying.
need
It's
to
not
be.
accurate because in that game,
It's as if they shot it stationary.
Yeah.
Okay. Alright. Okay, continuing. So let's see. A small satellite is in a parking orbit around the Earth. How far is it from the surface of the Earth? So let's calculate how far away a TV satellite is. We have the radius of the Earth and we have the mass of the Earth. So the nice thing is we can use Kepler's Law here. So there's the Earth, there's the satellite, and I want to know this distance here.
how many seconds in a day?
We
It's
can get,
T in seconds.
yeah, it's in seconds. Well, what's Kepler's Law? T squared equals
4
4 pi squared over gm
Oh,
or cubed, right? And we're looking, now wait, just before you type anything, the or will be gmt squared, right? Over 4 pi squared cube root. Now that's going to be this distance, isn't it? Center to center.
so you have to minus.
So I'll
the
have to-
radius of the-
Yeah, if I only want this distance, I'll call it x. It would have to be this minus the radius of the Earth. So this would be cube root, g you know, m you know. Yeah, you know all of these, don't you? Just make sure your t is in seconds. There's the numbers if you need them. You got that? You got the numbers? So can you put them into the formula? Sorry, what do you need, Gina? You need the numbers?
Can you go back to the formula?
Did you get an answer, Gina? No.
24 times 60 times 60.
Yeah, squared, all squared.
Yeah.
Minus.
Syntax
What's
error.
the radius?
There it is, there. 6371000.
6, 3, 7, 1, 4, 4.
Now the answer's going to be huge, so you might want to divide by 1,000 to make it kilometers.
5,
Huh?
2, 3, 4, 5, 7, 3.6 times 10 to the power 7.
So divide by 1,000, and what you get?
Oh, divided by 1,000?
Yeah.
3, no,
I got 42,228.
3.56.
Hang on, let's just write down yours first, Dorian, and then your Sax. What do you get?
3.56 times 10 to the power 4 kilometers.
So is that this?
No, it's more numbers than that.
Oh, oh, that seems really big. What did you get?
Something wrong.
42,228 kilometers.
228 km.
1, 2,
Now
3,
that
4,
seems more like what I thought the answer would be.
It's the same number. It's the same amount
Is
of
it?
numbers. Same amount of numbers.
Oh, same number of digits.
Yeah.
Okay, I'm sorry, but yours actually is a little bit different.
Yeah, maybe I did something.
Well, who else has an answer?
I'll do anything.
Diego, can you Google why they're calculating altitude of parking orbit?
Of?
Parking orbit.
Mass of the Earth is 5.47 times 10 to the 20.
Ah, there we go. 97, not 47. So-
4 bits.
Ah, okay.
So I think yours was right then, Dorian.
I already cancelled it out.
Oh.
Geostationary. Earth orbit.
Yeah.
I'll do it again anyways.
You got me kilometers.
7 times 10 to the power
300 kilometers?
negative
No, that's too small.
times n was what was n?
There you go.
5.97 times 10
No,
to
wait.
4
No, same also.
times what?
Did you put in 9.7?
Square
Yeah, it's about 25 hours or something.
42,228.
t squared. What did you get?
Oh, let's see.
That's my answer.
Let's see. We have a difference between the front and the back here.
Wait.
I deleted
Maybe
it.
I'll do it again. Maybe
Alright,
25
I'll type it in.
times 60 squared
Then we'll know.
over r squared.
I'm
Oh,
telling you,
sorry,
I
4
typed it in.
times
The constant is number 39. So.
Well, no, 30. No, wait.
squared.
So shift 7, 39.
Hold your horses.
30,000 kilometers
Hold your horses.
from sea level.
Where the heck is the power button on this? Gina, where's the power button? Like, oh, is this it? Oh, it is, okay. Power 24. Now we'll see who is right and who is wrong. This is terrible. Zach is right, nearly, roughly.
Really? Then where did we?
It's about 40. I got 41,600, but I didn't use the G constant. I typed it in manually. Yeah.
Why is only 2 zeros?
2 zeros?
And the last one, the R.
Oh. That's wrong. Thank you. Zach, you're the one who is wrong.
637
And you are the ones who are right. Well done.
Is it 0, 0, 0?
We both made the same mistake. We left out a 0 in our radius.
So 6317 0, 0, 0.
6. What is it? 3. Can you read it?
3.59 times 10 to the power of 7.
7.
Oh my goodness. Okay. Wow. We both. Yeah, we both pulled the Diego. Yeah. That's 4 Diegos in one class.
I think we are managing a new record.
We are. We're hitting new records here. Okay. Thank you up the front for getting that right. So the next example here is a bit of a long one, which I'll do this in the start of the next class. But before we go, there is something I want to show you which I think is quite interesting. So imagine you're here on Earth and you're looking at a faraway planet, and you can see that there's a moon in orbit of the planet. Okay? Now, what things could you know from just observing? Well, could you know the time of the orbit? Yes, you could. From just looking, you could see how long it takes the moon to go around the planet, right? What else could you know?
Well, that's assuming it's always in view.
But even not, you could infer it from even a sample. You know, if you see it does a quarter rotation in 12 hours, then you can, you don't need to actually see it go all the way around. You can infer it, right? What else could you know from looking at it?
What are you saying if we look at it
From looking at it in a telescope and collecting data, what things could you know about this? We could definitely, I hope we all agree we could know the periodic time.
Yeah.
Do we all agree with that? Okay, what else could you know?
How like in speed.
Yeah, well, you could know things like perhaps the speed or the radius here, for example. I don't think it'd be too difficult to work out the radius, because you did this in trigonometry using sine and cosine rule, right? Now, if you look at Kepler's law, he said t squared equals gm, isn't it, over 4 pi squared r cubed.
Yeah.
Now, could you know the time? Yes.
So it's other way around. 4 pi squared over gn.
Oh,
Negative.
there. Right. Could you know the time? Yes. Could you know the radius? You could. Okay. So we could know this, we could know this. We know this, and we know this, and we know this. So what could we work out? We could work out the mass. So this is how you could get the mass. Because I'm sure you must have wondered, how is it that you can say, oh yeah, the mass of the sun is this? Do you know? Or the mass of Jupiter is this. Yeah, I mean, you can't go there to collect samples. You know, you can't measure it, right? But you can work it out from looking at the orbit of its moons. You know. So really quickly, before we finish, we could calculate the mass of the sun. The mass of the sun. Hang on, I have this upside down, don't I? 4 pi squared over gm. Actually, is that what I was asking you to do in this one? Oh, it was. Okay, yeah, we'll leave that till the next day. We'll calculate it here. Yeah, okay. Can you try and finish those Kepler, no, not Kepler, Newton's questions at home, please? Thank you.